There we go. Okay. All right. It is time. I'm going to get started, even though the majority of the class is somehow missing. Might have something to do with the power fail earlier, may not. Um, so what we're going to do today is to revisit a little bit about what we talked about on Monday. But for the most part, we're going to move ahead to talk about something new. So I'm going to start with this part here of a more formal way to look at transformations or inference rules. Basically, they are the same thing. They refer to exactly the same thing. So the first thing we want to do is to look at a set W, which is defined like this. So the set W is basically the set of all the well-formed formulae. So you can see how beta here is such that beta is a well-formed formula. So based on a particular propositional system, W is just a set of all the well-formed formulae. Okay, so I'm gonna go slow and just kind of pause here. Do we understand what is a well-formed formula? So you need to know what is alpha, and you also need to know what is omega, because one defines all the alphabet, the other one defines the operators. So once we know those two, we know what should be in this particular W. So based on the discussion last time, we also know this set W is going to have an infinite number of elements. Now, are all the elements going to be interesting and make sense and useful? No. We're going to end up with a lot of well-formed formulae that are totally pointless. Okay, but nonetheless, they're still well-formed. So that's the set W, which is important. The next thing we're going to do is to claim that iota is a subset of W. Okay, so let's look at this statement here. Why do we know this has to be true? Based on how W is defined and based on the role of what iota is representing, why do we know I is a subset of W has to be true?
W is all of every well-formed formula,
Yep,
and in order for it to be an iota, it has to be
yep,
a well-formed formula.
exactly. Because iota is the set of all the well-formed formulae that are given to be true. So the first requirement is they have to be well formed. So that means every element of iota also has to be an element of W. All right, very good. So now we define a new set D, such that D is a set of well-formed formulae that are quote unquote derivable from well-formed formulae in iota. Now it may not be direct, okay? So this can take multiple steps, but the idea is using the inference rules in Zeta, we should be able to derive or to show that every single well-formed formulae in D, which is a subset of W, is true. Okay, so do we understand what D is representing? Every element of D is an element of W. Okay, that's one. Two, every element of D is also derivable from something in the iota. So it is by the use of the transformation rules. But the question is, how do we define D? In other words, this is the intent of the set of D, but how do I formalize um, what is inside D using the notations that we have at this point? So that starts with the next paragraph. Assuming that theta, phi, and psi are elements of alpha, each element E of zeta has the following format. So every single transformation rule, every single inference rule, so you can call it a transformation, we can call it an inference rule, you can call it a production, but every single one has two sides. This is the infer symbol. On the left-hand side of the infer symbol, we have a set M. On the right-hand side of the infer symbol, in this case, we have well-formed formula Q, and then it uses theta, uh, theta, phi, and psi as its arguments. So that's just a notation. That is just a notation. In other words, I am just picking up one element, okay? We call it E in this case, from zeta, and it's going to have this particular format because we need a set on the left-hand side to specify the constraints, And we need on the right-hand side a well-formed formula, which is based on what kind of symbol we have defined. So are we okay with that notation first? Because this can be the first obstacle of understanding the rest of this discussion. Okay, that's okay. So WFFQ has no particular meaning other than it's just representing a particular well-formed formula with a subscript of Q that takes three things, and however it arranges these three things doesn't matter. Okay, we just know that it is an expression that involves theta, phi, and also psi in this case, and that is explained by the following sentences. M itself is a set of WFFs that refer to uh, theta, phi, and psi. For example, an element of Z may look like this. So this entire thing, starting from here all the way to here, can be our element E. So that will make this set here, this entire set, is going to be the M, and then this implication is going to be the WFFQ of theta, phi, and psi. So this is just an example. Are we still doing okay so far in terms of the notations? I'm just trying to come up with a notation to say, okay, take one thing out of zeta, and we want to know what it looks like. Okay, what is the format of one of the inference rules from the set of zeta? Um, so I did add something, this semester. I gave you guys a link to Wikipedia, which has a list of the inference rules that people typically use. So we have, so sometimes they don't use the infer symbol. So instead they use, oh, actually they do use the infer symbol. Um, actually, this is not what I want to use. There's another Wikipedia page later on that is actually more relevant. So when we get there, we'll talk about that. Now we have the vocabulary to describe membership of D. In other words, now we can describe what does an element look like in D. First of all, by definition, iota is a subset of D. Then we can utilize inference rules as follows. So this is kind of like the base case of a recursion. In other words, this is where the recursion ends. And then there's a quote unquote recursive definition based on the following. So this is a big if here, and this is the then. So we have to understand the condition before we can quote unquote fire the rule. So the conditions is, the first thing is we're going to pick three things from W. In other words, we're going to pick three things that are already well formed, A, B, and C, but not necessarily from D. So A, B, and C, there's no requirement that any one of A, B, and C has to be coming from D. They just have to be well formed. So give me three well formed formulae, and we'll see what we're going to do about it. The next line, or the next bullet item, says there exists a T, which is an element of zeta. In other words, we are just calling a particular inference rule as lowercase t, such that t equals to m inverse WFFQ using theta, phi, and psi. Okay, so up to this point, I'm simply saying, okay, what are the ABCs? A, B, and C are all well-formed formulae. What is T? T is really just one of the inference rules that we pull out of the set zeta, and it has the left-hand side is M, and then the right-hand side is represented by WFFQ of theta, phi, and psi. Are we still doing okay so far? So right now, I'm just describing what do I have in my tray. I haven't even started to talk about how these things are going to be applied, how they relate to each other, nothing like that. I'm just describing what is on the tray right now. The next one, now it becomes important. It basically says every element of M is going to be a well-formed formula itself, and every well-formed formula is going to be expressible by this kind of format: WFF, phi, theta, and psi. So this WFF has nothing to do with this WFFQ. Well, okay, I shouldn't say nothing, but they're not the same thing. This one here is representing one element from the left-hand side of the infer symbol. Okay, so I'm going to pause here because right now, there can be confusion. So I'm going to use an example to illustrate what I mean by that. So if you consider T to be this entire thing, then this entire side is M, and one element of M can be this one here, can also be this one here. That is what WFF is trying to refer to. It's just one of the patterns in the set on the left-hand side of the inference. Are we okay so far? Okay, because I want to make sure that we go kind of slow and make sure it's step by step so we have no question about what each symbol is representing. So now that we know what WFF, not WFFQ, is representing, then we have a requirement, okay? So this is the part where we start to make connections between all the parts on the tray at this point. All the way up to here, I'm simply describing what is on the tray. What are the things that we're trying to talk about? But now we're trying to relate things. So this part here, WFFABC, is an element of D. It's like, okay, wait, hold on a second here. How do we go from theta, phi, psi to A, B, and C? Theta, phi, psi were used to describe a schema. They're schemata, which means they're placeholders to describe a well-formed formula that has placeholders. A, B, and C are specific well-formed formulae in W. That is the difference. So the connection between this part and this part here is simply WFF. WFF gave us the structure of what the expression looks like, how we are using these three things in the structure of WFF. We want to apply the same structure to A, B, and C. But A, B, and C are not placeholders. Each one is a specific well-formed formula that is in the set of W. Are we still doing okay so far at this point? All right. A, B, and C do not need to be in D. They just have to be in W. In other words, A, B, and C only need to be well-formed formulae. But WFF of A, B, and C needs to be in D. Okay, so let me pause here. What is the difference between the set D versus the set W? W is easy. It is simply syntactically correct. Okay? What about D? What about an element of D? What qualifies to become an element of D? It also has to be true, right? Or at least up to this point, it is known to be true now. Okay? So this is basically saying we don't care about whether A, B, and C are true or not. It doesn't matter. But when we apply A, B, and C using the WFF here, that needs to be true. Is that okay? And we're trying to do the same thing for everything in M. What is M referring to? M is referring to everything on the left-hand side of the inference, of the rule that we have just randomly picked up from Z. Is that okay? So this statement here, or this particular condition, is simply saying, I have found a way to instantiate every single pattern on the left-hand side of an inference. Is that okay? Does everybody understand what that statement means? When you look at M itself, M is going to look like this. It is simply describing a pattern. It uses placeholders because all the Greek letters are basically placeholders. So it doesn't really quite say, no, that well-formed formula can take the place of theta, and then this one over here can take the place of phi. But if you have something that takes the place of phi, it will take the place of this phi as well as this phi over here. That makes it a constraint. It's a requirement in order for everything on the left-hand side to be satisfied. And then you also need to pick up something for psi so that theta implies phi is something known to be true at this point, and then phi implies psi is also something that is known up to this point. If you can meet that requirement, if you can find something, if you can find the three well-formed formulae to make this true, then we can quote unquote fire the rule. So that's when we move on to this part here. Then we can quote unquote fire the rule or fire the inference rule. By firing the inference rule, we have now established that WFFQ of ABC, which is on the right-hand side of the inference, is also going to be an element of D. Is that okay? The ironic part here is by using these symbols, by using the there exists for all, and then using these symbols to basically identify different parts of the inference rule, the rationale behind this is to make it clear of what D is, what is set D. But the ironic part is it takes a lot of energy to read the notation to really understand what it means. Is that okay? So now the question is, so if it is, so are you so the question from some of you to me is, are you intentionally trying to make things difficult to understand? What is the whole point of doing this when you can just verbally say D is the set of all the well-formed formulae that can be derived from iota? So the question is, why don't we just use that one single English sentence instead of using all of these symbols to define the same thing? You have to think about what your math professors would have to say. Yep.
The whole point is that we're building from the ground up, right? So it's like, these things don't have meaning until we give it to them.
Yep. And we don't, yeah, go ahead.
Yeah, but saying that doesn't inherently mean anything unless you have a way to prove it as true based on this.
Sort of, because we are not trying to prove anything is true. We're simply trying to describe the set D in this case. But if I just you just verbally describe it, like what I said earlier, D is a set of all the well-formed formulae that can be derived from iota. That can be interpreted in many ways. This, on the other hand, cannot be interpreted in many ways because the way we define the existential quantifier is very specific. In fact, we had an algorithm, we had the pseudocode of an algorithm to specify, well, what does it mean when we use there exist? What does it mean when we use for all? We actually have algorithms to very specifically define those operators. So this is the way that we try to define something to the point where there should be no ambiguation whatsoever. Now, is it hard to read for someone who's new to these symbols? The answer is yes. Okay, I do understand that part. But once you get used to it, it's a very precise way of expressing how things relate in terms of mathematical concepts. Are we good so far? It's kind of like a programming language, right? So do you want a programming language that reads like natural language? I can see lots of people just turning their heads. Why not?
Because it's not always 100% like defined. It's not definitive.
Well, if it's not definitive, if it's not definitive, we can try to have your compiler to guess what you actually mean. What about that? Would that be a good idea? Why not? Let's say you turn in a program, a program that by our standard has a syntax error, and the compiler looks at the syntax error and go like, well, instead of reporting this as an error, let me guess what you actually meant. Why would that not be such a great idea?
Because it's going to lead to it doing all kinds of crazy things rather than just not running and telling you something's wrong.
Exactly, because you're not sure that the compiler would try to interpret it the way that you intend, right? And it's the same thing with mathematical notations. because we don't want to leave anything to ambiguation.
It also has the benefit of not depending on what language somebody speaks. So you can use it to convey mathematical concepts between people who speak different languages.
Yep, because math itself is a universal language, sort of. Yep, that is correct. All right, so that's just an example of how I used the symbols that we have defined up to this point to describe certain things here. The next main section is a quote unquote useful example. And we have started with this one last in the previous class already. Um, so I gave you some examples, but today I will skip over all the other stuff. And instead, I'm going to click on this link here. It's also a Wikipedia link, but this time it does have the correct um, inference rules. So the inference rules, this is one inference rule. They do not use Greek letters. They really should be using Greek letters because in this case, the P, Q, R, they are all placeholders, and all the placeholders should be using Greek letters. So just kind of imagine those are Greek letters. But the idea is I want to show you how many rules there are. Okay, the first one is something that we have not seen yet. It says P implies Q and P implies not Q implies not P or infers not P. Okay, so does that make sense to you? What this means is if I can find the pattern of P implies Q and I can find the pattern of P implies not Q, these two are known to be true. That means infers, okay? Infers is basically a syntactical derivation, but there's usually a soundness to it. It infers that P has to be false. Does that make sense to you? Well, think about it, okay? Think about it a little bit. In what do we need to do to make an inference true? Not inference, sorry, I take it back. What do we need to do to make an implication true? The single line arrow here is our double line arrow, which is implication. So there are three ways to make an implication true. There are two ways that are kind of like the same, which is the left-hand side of the implication is false. Okay, we got that. And then the third way is to have both sides being true. So those are the only three ways to make an implication true. So in this case, if you are given, okay, if somebody tells you that P implies Q is true, P implies not Q is also true, well, the only thing we can now infer that P itself has to be false. Because if P itself is true, then one of these two implications has to be false, and they cannot be on the left-hand side of the inference. Is that okay? So that's one of the rules. This is negation elimination. So negation elimination starts with if I know that P is false to begin with, it infers P implies R has to be true. Well, that's something that we just talked about, right? Because if P is known to be false, then if it's on the left-hand side of an implication, then the implication has to be true. So these are the rules that people use when they apply logic to try to prove something. And there's a whole bunch of rules. So we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. Okay, so there are 12 of these inference rules. And there's a whole bunch more here because they also have to take into consideration commutation. Commutation means you can reverse the order. So there's a whole bunch of these rules. And we talked about this last time too, is when you try to prove a theorem, how do you know which one to use next? Because there's at any time, there's a whole bunch that are probably applicable at the same time. So which one are you going to use? Who knows, right? And this is a tough problem, okay? This is a tough problem. If you want a system to automatically prove theorems, and you have this many rules, and there's no limitation as to the size of W, the set of W, then we have a problem. And that's not something that we want to deal with. Are we okay so far? This is kind of echoing something that I said on Monday. All right. So now we are going to take a segue and we'll talk about something that seems to be unrelated to what we are dealing with here. So I'm going to skip over a bunch of stuff here, which is completeness and soundness. We'll get back to this one when we are done with resolution. So this is the derivation of resolution. Itself is the derivation using Boolean algebra. So I will just briefly describe how I applied Boolean algebra because you will need to learn Boolean algebra in this class too. All right, so the first line, how do I establish that the left-hand side equals to the right-hand side? Which rule did I use? Or what definition did I use in this case? This is actually more of a definition than it is a rule. And I also have to give you the additional information that conjunction has a higher priority compared to implication. So you can kind of imagine there's an extra pair of parentheses from here to here. So given that, why I can derive it from the left-hand side to the right-hand side on the first line. Yep.
You use the definition for implication?
Yep, that's it. I used the definition of implication. P implies Q is exactly the same thing as not P or Q. All right, so that's just one of the one way to look at implication. From the first line to the second line, what rule did I use in this case? Actually, this one has, I think I did several things at the same time. The first one is De Morgan's law. De Morgan's law takes the negation of an and turn it into the negation of each component in the original and change the and to an or. That is De Morgan's law. Are we okay with De Morgan's law? Do you guys want me to write out De Morgan's law just kind of on its own? That can be helpful. Okay, so I'm going to put it on the whiteboard and not journal. So De Morgan's law says, so in this case, I just use A, B, and C as patterns. So it says, if you negate A and B, it really is going to give you exactly the same thing as not A or not B. That's the first part of De Morgan's law. The second part looks exactly like the first part, and the ors are exchanged. So if you take the negation of A or B, it really is exactly the same thing as not A, but this time and not B. That is De Morgan's law. I think we described this earlier in the semester, and I described it as the quote-unquote distribution of negation, because this negation is applied to the outside of the entire thing, of the conjunction, and you can see how, quote-unquote, the negation is distributed to the components of the conjunction, but you cannot keep the conjunction anymore. The conjunction has to turn into a disjunction. That's De Morgan's law. And is anyone wondering, I look at this and it doesn't seem to make sense. How do we know this is right? Just in case somebody is wondering, okay, what would be the answer to that question? How do we know this is right? What technique would you use to basically say, yeah, I can prove this? What technique would you use?
Truth table.
The truth table, very good. Okay, so exactly, okay, you can use a truth table because A and B are independent variables. You have 4 rows in this case. So what you need to do is to have the 4 rows, 1 column for A, 1 column for B, 1 column for the left-hand side of the equality, and 1 column for the right-hand side of the equality. The 2 columns corresponding to the left-hand side and the right-hand side of the equality, they should be the same for every single row of the truth table. But this is something that you can do, okay? If you don't want to do it by hand, you can use a spreadsheet to do it. I think I have already shown you guys how to make a spreadsheet, right? So you can use a spreadsheet that quite easily you prove to yourself that these 2 rules, the De Morgan's law, they make sense. They actually work. So getting back to the derivation here, De Morgan's law is applied to this negation of this or. Nope, I take it back. It is applied to this negation of this and, ending up with the negation of the first component or the negation of the second component. The dissolving of these parentheses has to do with associative law, so they're not needed. And then from here to here, I use De Morgan's law again. So this time I apply De Morgan's law because I have a negation of an or, then it turns into an and, but each component itself is negated. Same thing over here. I have the negation of an or, so now I end up with an and with the negation of each component. Not psi is psi, not rho. Are we good so far? Okay. And then from here to here, I am using the identity rule. In other words, one or true is the identity of conjunction. So you can always say and true after anything, and it won't change the meaning of the original thing. Is that okay? And once again, these rules, each one can be proven using a truth table. So if somebody is not convinced that psi is really the same thing as psi and true, you can use a truth table and rather easily prove that those two are equivalent. And then we do the same thing with rho on the other side. And then from here to here, I look at the true and go like, oh, there are many ways that I can come up with a constant of true. One way is simply to pick something and say that thing or the negation of itself. Okay, so I apply this, I change this one to, in this case, psi or not psi. And then this one, this true, is also turned into psi or not psi. And then I applied distribution. So and is kind of like multiplication, or it's kind of like addition. So I am distributing, I'm using the rule of distribution. So we end up with psi, no, this is phi and not psi, or phi and psi. Are we okay so far about the use of distribution? And then the same thing on this side here. And then on the next one, I reordered things a little bit. And then I applied factoring. Okay, so I combined a few steps into one, so that's why it's a little bit harder to read. So we have not phi and not psi over here. And then over here we have phi and not psi. So when you look at this guy here, and also this one over here, you can see how not psi is common, and then the other two are not common. So I use factoring to combine those two into one. And this is the same thing. I look at this particular conjunction, and then I look at okay, we need rho in this case. So we look at this conjunction here, and then we do the factoring again. So we end up with this particular expression. The other two I did not do anything about. Okay, so they're just kind of left alone and continue to be the way they were. Are we still following the algebra here? This is Boolean algebra. Okay. And then from here to here is a simplification, because if you have anything or the negation of itself, it is guaranteed to be a true. Same thing over here. You have something or the negation of itself, it is also guaranteed to be true. And then we have another simplification, because one and whatever is just the whatever. And then same thing over here. Whatever and one is just the whatever. Are we still doing okay? All right. And then from here to here, I use another simplification, because when I look at this, I have the negation of psi or psi itself. So that combined to basically a true. But then when you have true to begin with, and you have a disjunction, then the whole thing is going to be true. True or whatever is true. Once you have true in the disjunction, you cannot turn that expression to false anymore. So that's the whole thing. So after this entire thing, what is the whole point, right? Other than this is an exercise of Boolean algebra, what is the whole point of doing this? The whole point of doing this is now we have a theorem. What theorem are we talking about? This, the first one here, that is our theorem. That implication is always true, no matter what you choose as your phi, psi, or rho. Are we doing okay so far? All right. So now that we know this implication here is always true, how is that going to help us? Well, you look at the two sides of the implication, and you will notice something. On the left-hand side of the implication, we have three things. We have three placeholders here. We have phi, we have psi, and then we also have rho. We have three different expressions or three different placeholders. On the right-hand side, we only have two. So the placeholder that we call psi, which has to be on one side non-negated, and it has to be negated on the other side, when we apply this implication, it completely disappeared. Now, this is the kind of inference rule that we like, because it starts off with something that's more complex, and it becomes something simpler. So if things always go from more complex to simpler, that means eventually we'll get to nothing. Well, okay, almost nothing. So are we okay so far with the resolution itself? This is called the resolution logic, which is just this part here. The rest, which is this part here, is the proof that resolution logic makes sense. It is the proof of resolution itself. So we're good here? All right. So now we're going to say, let's turn it into an, okay, this is actually kind of important too. This is based on the meaning of conjunction, disjunction, implication, and so on. This at the bottom here, that becomes syntactic. In other words, the computer really has no understanding like we do of what is implication, what is conjunction, and what is disjunction. When it's trying to prove a theorem, it just looks at and, the operator of and it says, oh, okay, that's just an operator. It looks at the symbol representing or, and it just goes like, well, this is just a symbol. It doesn't understand the meaning behind what is an and, what is an or, what is an implication. So syntactically, this is what a computer does. But semantically, that's what humans do. So let me make sure that we understand, one part here, which is the top part here, that is for us, okay? It's for people who understand the symbols, the semantics. The bottom part, which is down here, that is for the computer. It's just converting everything into syntactic operations. It's just pattern matching, okay? If I can match this pattern, and using this particular psi, I can also match another pattern like this, and both of these well-formed formulae turn out to be known to be true at this point, I can apply this rule. And syntactically, I'm going to take the placeholder that was called phi, I'm going to pick up the placeholder called rho, and now I can say, oh, by the way, this simpler disjunction is also going to be true. That's what the computer does. It doesn't really understand the semantics or the meaning of the operators. It is simply doing pattern matching. Are we okay so far? So we turn a theorem into a inference rule because it makes sense. Is that okay? But then somebody can argue, but there are tons and tons of theorems that we can prove. So does that mean that we just end up with a whole lot more of these inference rules? The answer is no, okay? Interestingly, the answer is no. This is the only one we need. So I am proposing a new propositional logic system where the only inference rule of any importance is this one. Now you still need the ones to do the commutation, to exchange the position of things. But that one is not really needed because the way we write programs can take care of that without using the use of extra production or inference rules. But this is the interesting one. All right, so that's the first ingredient to proving theorems mechanically, is the inference rule. I mean, resolution rule, the resolution logic. Any questions about resolution itself? Okay, then we move on to the second concept. Because if you cannot express everything as a disjunction within, as a well-formed formula, then we have a problem, okay? Because then we cannot apply this. So what if some of your well-formed formulae is not an or? Then this rule cannot possibly apply because it requires both of these patterns or both of these well-formed formulae to be disjunctions. So the next question is, can we convert every normal, quote unquote, normal Boolean expression into just a bunch of ors ended together? Let me describe that with a picture, okay? It makes it a little bit easier to understand. Can I erase De Morgan's law? So the question is, if you just give me some random Boolean expression, can I turn that random Boolean expression into a format like this? We have one conjunction at the top. This is the last operation, but it's ending a whole bunch of components. Each component is an OR. What can it be ORing? Well, it turns out there's another restriction here. What each OR can do is simply to refer to either things that you can find in alpha or the negation of those things. All right? Let me say that one more time. We have this really strong restriction of, we want to convert everything into this form. What is the form? It is one conjunction of a bunch of disjunctions, and then each disjunction can only have things like elements from alpha or the negation of an element from alpha. So if alpha has P, Q, R, then you can have P, you can have Q, you can have R as components being ORed. You can also have not P, not Q, not R, or any mixture thereof, inside each disjunction. Is that okay? Does everybody understand what I mean by that? Okay. All right. So this is where you guys can give me an exercise so I can illustrate the concept to you. So let me switch to a slightly different tool. I think I can just use a text tool in this case. So let me go to mousepad. And you guys can give me a somewhat simple, because we don't want to spend too much time to do this. You can give me a Boolean expression, just any Boolean expression, but you have to use parentheses because otherwise I don't know the order of the operation. So give me something fun to do. Like it has to have implications and nested stuff, negation somewhere and so on. Just give me some random stuff. I mean, you guys, each person can contribute one little thing. We'll just say that we have 3 variables, or we can have 5, okay? We have P, Q, R, S, T as individual variables. In other words, P, Q, R, S, T are in alpha. And you can use conjunction, disjunction, implication, negation, and you can combine these things in any order you want. So I'll just try to hook people and go like, okay, give me something. It only has to be simple.
Not P and Q implies R.
Okay. So do you mean this?
Yeah.
Okay. Do we want to make this more complicated because you guys can build on top of this? Yes.
Or not R times Q?
Okay. So we have an or.
Not R times Q?
not RQ, like that? Or do you want the OR to only apply to the not R and then the whole thing and Q?
What you tell.
Okay, so that's good? Okay, so we'll start with this, okay? So I make this claim and say, I can convert this into something that looks like this, starting with an and, or the last operator is an and then each thing is anding, is an or, and each thing inside the or is either a variable, a PQRST, or the negation thereof. All right? So let's go ahead and see how we can do that. All right. So the or is not really that big of a deal, okay? Because I can use distribution to quite easily get rid of the or. So the first task I need to do is to get rid of the implication, because implication is neither nor and. So that's the first thing I need to get rid of. So the first thing I need to do, okay, this is easier because I can now highlight which portion I'm working on. This is what I'm going to work on first. Okay, I want to get rid of the implication operator. So now I can say, okay, I'm going to take this equal and put it under. This way things can align a little bit better. So that means I can now say this is not P and Q or R. And I'm going to put extra parentheses even though they are not needed. And then the rest, I will stay the same. Is that okay? This is just using the definition of implication. So I'm on the side here, I'm just going to say by the definition of implication. All right, the next thing I can do is to use De Morgan's law, because I know that every time I have a negation of an and or a negation of an or, that's going to be a big no-no. I cannot do that, because in the end, I can only have negations inside the ors of individual variables. So I know if I see an or of the result of an and, or if I see the not of an and or the not of an or, I need to use the distribution known as De Morgan's law and move those negations all the way in, so that we end up only applying negation to variables. Okay, so now I can say, okay, I can apply De Morgan's law. So now I end up with not P or not Q, that whole thing or R, and then the rest are unchanged. And I will say by De Morgan's law. There we go. All right. Are we okay at this point? So let me highlight which portion is changed. This OR is maintained. It was the same as before. So what I did was I changed the negation of not P and Q and turned that into not P or not Q. In other words, I applied this negation to each component. This is one component, this is another component. But by the application of De Morgan's law, the and between these two is now changed to an or. So is that okay? Yes? Okay. All right, so what do I need to do next? Well, I can do one little simplification because saying not P is unnecessary. So I can now say P or not Q, and I dissolve the parentheses because of the associative law. I can now dissolve that parenthesis. And I can dissolve some more. Well, so I can now dissolve, and not R over here, not R and Q. Are we good so far? Okay, it looks like we're getting close to what we want, but this is not exactly what we want. Okay, it is quite opposite to what we want. This is called the disjunction normal form instead of the conjunctive normal form. This is opposite to what we want, because what this is representing is the overall of an or, and then one is oring. Each one is a conjunction, which is opposite to what we want. That's okay. We can fix that. So the question now is, can I simplify this any further? There are probably ways to simplify that some more, but I'm not going to do that. Instead, I am going to regroup things a little bit. So P or not Q or R is on its own, and then we have not or, not R and Q on its own. In other words, this is just the application of the associative law, which means you can put parentheses anywhere you want, because if you think about addition, it looks like addition, but it's not. But if you think about just regular addition, it doesn't matter to which order you apply the addition, right? If you just have a bunch of additions, whether you apply this first and then apply this and then apply the overall, or you apply it kind of sequentially, it doesn't matter because of the associative law. So I just use associative law to regroup which bunch we look at one thing and which bunch we look at something else. So at this point, I'm going to use distribution. Yep.
There's a typo.
Oh, not Q?
Yeah, not
Right. Okay. Thank you. All right. So at this point, I'm going to use distribution. In Boolean algebra, there are two distribution laws, and not just one. So in Boolean algebra, if you have A and B or C, it is the same thing as A and C or A and B or A and C. So this one you're familiar with because normal algebra also has this. But the other one is A or B and C can also distribute. So in this case, you end up with A or B and A or C. Now that would not work with normal algebra, but in Boolean algebra, it works. So once again, if you look at this and go like, that looks really odd. I'm not sure that's going to work. What is the answer? Truth table. So you use a truth table, and this time we have 3 independent variables, right? So you end up with 8 rows in this case. And then for each row, you list what is A, what is B, what is C, and then you evaluate the expression to the left of the equality, and you also evaluate the expression to the right of the equality. And these two expressions, they should be the same for every single row of those 8 rows. Are we okay so far? In fact, let me just do it one time here, okay? Because I know there are people looking at this and go like, that doesn't make sense. It doesn't make sense because in normal algebra, using numerical values, it does not work. However, in Boolean algebra, it does. All right, so I'm going to use my typical thing, which is really just binary numbers, okay? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, oops, 1, 1, 0, and then finally we have 1, 1, 1. All right, so this one is just a 0, and so is this one. C is true, but B is false, so this is going to be false. On the other side, because A and B are both false, we have one false in the conjunction, so the whole thing is going to be false. In this case, well, B and C are interchangeable. They're just going to reverse of each other, so we know this one is going to be false and false too. All right, so this time we have a true, and we also have a true here. This time we have a true here. We also have a true here. Well, in fact, if A is true, then we already know the whole thing is going to be true, so we can just fill the whole thing quite easily over here. There we go. So at this point, if you just did the actual logic yourself, and verify each individual 0 and 1, then you can see how A or B and C, the whole thing, versus A or B, the whole thing, and A or C, the whole thing, they turn out to be exactly the same. All right? That's the proof. You cannot prove axioms like this in regular algebra because there's an infinite number of integers. So you simply cannot just say, I'm just going to enumerate every single possible case and prove that. But in Boolean algebra, we can do that. All right. So how is this going to be helpful? We are specifically going to use this rule here. In other words, I am going to look at this as my A. I'm going to look at this as my B, and I'll look at this as my C. Is that okay? Does everybody understand how I'm going to apply the second distribution law to this particular format here? All right. So let's see what we're going to end up with. So we have P or not Q or not R. And the other one is going to be P or not Q or R or Q. Is that okay? And well, the way you guys set it up ends up with something that's always true because we have R or not R in here. So that means this whole thing, okay, I'll do step by step, really, really step by step, because now we have this. Because when you have R or not R, one of these two has to be true, but then the other one would be false. That's okay. We just need one true for the entire disjunction to be true, right? So now we can conclude this whole thing is true. The other side has not Q or Q because we have this not Q over here and then we have a Q over here. Once again, one of them has to be true and the other one has to be false. But since we have a disjunction of stuff, if at least one is true, the whole thing has to be true. So I'm just going to make it really step by step, like so. And now we have a true in each disjunction. So this whole thing is going to be true. This whole thing is also going to be true, which also means the entire thing is guaranteed to be always true. You guys just so happen to pick an expression that is always true. That's just a freak accident. But the whole point is, um, I did end up with a CNF. I did end up with a conjunctive normal form. By the time I got here, this is conjunctive normal form because we have a disjunction of two things. Each thing being ended together is a disjunction. Each disjunction only involves either variables or the negation of a variable. So it does fit the form of a CNF or conjunctive normal form. Is that okay? Now, is this the best and easiest and the quickest and most direct way to get to the CNF? I'm not sure. Okay, I just kind of picked out the steps, as I went along. But the point is, we got there. So the claim that I'm going to make is it doesn't matter what Boolean expression you give me as long as it is valid. In other words, as long as it is well formed, I can convert that into CNF. Is that okay? It's just a claim at this point, okay? I'm not proving, I'm just claiming at this point. So assuming that can be done, how is that going to help us? Well, if everything looks like this, now this is a conjunction, right? Look at this part here. That is a conjunction right there, which also means the left-hand side of the conjunction is true, the right-hand side of the conjunction is true. So in propositional logic, we just put this by itself as an element in what we know as W, and also in D in this case, if it is known to be true. And we also put this by itself, as one well-formed formula in W. Because everything that is known to be true in D, there's an implicit conjunction to basically say this and this and this and this and this are true. Are we okay so far? All right. And I'm looking at the time because I need to determine what is the next topic. So I'm going to skip over the mechanical part of how to convert any expression, any Boolean expression into CNF, and I'm going to go straight to proof by contradiction because I want to give you the overall idea of how these things are supposed to connect together instead of giving you a bunch of pine needles, too many pine needles. So the next major piece is called proof by contradiction. So I'm skipping over the completeness for now. We'll get back to it. And also the example. So now we're going to go to proof by contradiction. So proof by contradiction, just like resolution, it starts off with some um, with one expression here. So the expression says P implies Q, the whole thing is implying P and R implies Q and R. In other words, if I know that P implies Q is true as an implication, then I automatically can say that doesn't matter what you choose as R, P and R, that whole thing, is going to imply Q and R, the whole thing. That implication is also going to guarantee to be true. I can't really highlight here when it's in this format. So this thing here, if this is true, then we know this also has to be true. That's a claim. How do we know this claim is actually true all the time? No matter what you choose as your P, Q, or R. Now, one way to prove this is once again a truth table. But in this case, if you make a truth table out of P, Q, and R, then you get a 1 for every single row. Because I said it doesn't matter what P, Q, and R are, it's always going to be 1. It's always going to be a true. But the other way is to prove it using Boolean algebra. So I'm just looking at the time. I'm debating whether to explain each step. I'll go ahead and quickly explain each step here. From the first line to the second line, it's by definition of implication, also by definition of implication. So I'm taking care of this implication as well as this implication over here. And then from the second line to the third line is also by definition of implication. I'm taking care of this implication this time. From the third line to the fourth line, it is the application of De Morgan's law. This is the negation of an or. It became the negated version of each component, but then the or becomes an and. And on the other side, it is just me dissolving all the parentheses whenever it's possible. And then from here to here is dissolving the parentheses here and here, because this is a big OR of something, and this is an OR by itself, so I dissolve this pair of parentheses without any problem. From this line to this line, oh, we just explained that one. And then from here to here is the identity. I can always introduce the identity of one in a conjunction, and I do it to both of these. And then from here to here is the true is re-expressed as Q or not Q. This true is also re-expressed as Q or not Q. You can see this is a technique that I use quite a few times already. And then from here to here is to regroup things, okay? So things line up a little bit better. And then from here to here is, let me see, what did I do? No, from here to here is rearranging things. From here to here is the distribution. So we have the distribution because we have an and of a disjunction. We have an and of a disjunction. So I just do the distribution. We end up with the and or the other and. From here to here is commutative, which means I just change the ordering of things a little bit. And then from here to here is just trying to find out what I did here. Oh, okay. So from here to here, it is a simplification of some kind. I can see how not Q is common to these two, and then each one has a P, the other one has a not P. So one way to derive this one here is are two steps. One is factoring, followed by simplification. And then same thing with this and one here, because we have Q or not R, and then we also have Q and not R, or Q and R. So by factoring, I can single out the Q, and then we end up with the not R or the R, which is a 1, which is true, and that's why we end up with this 1 over here. And then okay, so at that point, we have this one and not q being just not q by itself, this q and one being just q by itself. So now we end up with not q in the disjunction as well as q in the same disjunction. So the whole thing simplifies to true. Okay, so that's kind of the mechanism. So what is the whole point here? Well, this by itself is not a theorem. It is called a corollary, which means it is kind of like a smaller theorem, which by itself is not really that useful, but it is used to prove another theorem, something that's bigger. So now we look at this and we say, excuse me. So now we start with this, okay? So let's just say that we have this implication, which is psi implies phi. Okay. You can pick anything to be the psi, pick anything to be the phi. But if this implication is true, then we also know that the following line has to be true. That has to do with the corollary that we just proved earlier. Is that okay? So let me show you the corollary, and then you guys can see, hopefully you can see the pattern. So this P here is a placeholder, which is replaced by psi in this case. This Q here is also just a placeholder, and it is replaced by phi. Are we good so far? Okay. So the question is, what did I choose to replace R as a placeholder? I chose not phi to be my R here. Is that okay? Because I want you guys to see how I applied the corollary in the proof here. So if I choose not phi to be the R here, that should not change the conclusion. Okay, this conclusion should not change depending on what R is. But I just so happen to choose not phi to be R. So that means now we are saying that if psi implies phi, then we also know for sure that psi and not phi is going to imply phi and not phi. Except in this case, you look at phi and not phi and go like, hey, if phi is true, then not phi is going to be false. If phi is false, then the whole thing is going to be false anyway. So that means there's no way out of this conjunction. It has to be false. Is that okay? This conjunction here has to be false. Is that okay? So that means I can now get to the final conclusion here, which is psi and not phi implies false. Okay, but the implication itself is true. So if this implication is true, and we already know the right-hand side of the implication is false itself, what is it saying about the right-hand side of the implication? No. It has to be false. This is the great thing about Boolean algebra is if somebody says, it has to be this, and that turned out to be wrong, then the answer has to be the opposite. So it has to be false because according to the truth table of implication, if we know that the implication itself is true, there are 3 cases where the implication can be true. The first 2 are easy because if the left-hand side is false, then we don't really care about the right-hand side. The third one says both sides have to be true, right? In this case, we already know the right-hand side is false. So that means the third way of making the implication true is not going to work. It has to be one of the first 2. So which one of the first 2? Well, we don't have a choice. The right-hand side of the implication is already given to you as a false. So that means if this implication itself has to be true, the left-hand side has to be false. The conjunction between psi, not phi, has to be false. Is that okay? And you guys are going like this, well, I can see how we are kind of playing with symbols and putting this over here and putting that over there and end up with something like this. So what is the big deal? The big deal is phi is representing the theorem that you're trying to prove. Okay? So you're trying to prove a theorem, and that is represented by phi in this case. Psi, on the other hand, is the conjunction of everything that is known to be true to begin with. In other words, it is a conjunction of everything in iota. Is that okay? That's the intention of what each symbol is representing. Once again, psi is representing a conjunction of everything that is given to you known to be true, all the facts. Phi, on the other side, is something that you're trying to prove. You're trying to say, hey, if everything that is in psi is true, then phi also has to be true. So instead of going for a direct proof, you can now go for a proof by contradiction, which is a little bit indirect, because what you're trying to do is to say, let's just say the theorem is false. If I combine that with everything that is known to be true, let's see what happens. That is proof by contradiction. Is that okay? So we got 5 minutes left, about 5 minutes. I can use this technique to prove the pigeonhole principle. I described the pigeonhole principle last time. You have n. Okay, so I'm just going to write it down. I think it is somewhere in the notes already, in the module already. So I'm just going to use the whiteboard to interactively describe it. You have n pigeons. You have m holes. And so this is given to you, okay? And so is this. We have at least as many pigeons as there are pigeonholes. In fact, we have more pigeons than there are pigeonholes. It has to be greater than. Is that okay? So these are facts that are given to you. And and then Tech has this crazy theory of, in the evening when all the pigeons come home, at least one pigeonhole is going to have more than one pigeons. That's my claim. And then you guys go like, I paid a lot of money for this class. How can you prove this? Okay, I don't want you to give me just some junk and some non-truth, right? So you want me to prove it. So how do we do it? Okay, so I'm trying to say this implies at least one pigeonhole has more than one pigeons. There we go. Okay. This is the theorem that I'm trying to prove. This is given to you as facts to begin with. This is what I'm trying to prove. So how does it fit into this thing here? The psi is this whole thing here. The phi is this whole thing here. Is that okay? Because I'm trying to give you a concrete example of how to apply proof by contradiction. All right? So I'll be okay with the setup of the proof. I haven't done a single thing to prove it yet, okay? I'm just trying to tell you which part is given to you as true. Do not ask me why that is the case. And then the other side is is implied by the first part, okay? It is a truth that should be true. If this is true, then that should be true as well. But we don't know whether this logic holds or not, okay? At this point, we do not know. Yep.
Would it be just greater than, not equal to?
It's greater than, this is greater than.
On the other side, would it just be greater than? Because that would say that it can be one as well. Would that be
Yeah, but if I make this equal to, then that also has to be equal to. Yep. So we can generalize. I mean, okay. Yeah. So minor little points. Yep. But you're correct. We can. If this is greater than, that has to be greater than. We can show it's greater than. But if it's greater than, it's automatically greater than or equal to. So we are still okay.
Because I was going to say that was going to be true. For each one.
Right. Yeah. The way that I had it would still be correct like this, because the implication is only going in one direction, but not the opposite direction. Yeah, But for now, we'll just say greater than or equal to both on both sides. So how do we prove this? I mean, just intuitively, it makes sense, right? You have more pigeons, or at least as many pigeons as there are pigeonholes. So that means when all the pigeons come home, each pigeonhole should have at least one pigeon in it. But it's hard to actually prove it directly. It's hard to formulate a direct proof, but an indirect or proof by contradiction is easier. So how do we do that? The first thing we need to do is to negate this side. So when we negate this side, what do we end up with? Well, let's think about it. When we say there is at least one pigeon in every single pigeonhole, it's the same if we negate that. If we say it is not the case that there is at least one pigeon in each pigeonhole, what is the easier way to say that? Mm-hmm.
Is less than one?
Okay, but you have to remember the quantifier. Because if we say at least one pigeonhole has this, the negated version of that is going to be, this is an existential quantifier. So when you negate an existential quantifier, what do you get? You get a universal quantifier with the negated predicate.
Would be like none of, then you would take it to like none of the pigeonholes have more than one?
That is correct. Have, well, you negate this one here, so that means it has, you basically say all the pigeonholes has
Less than or equal to one.
less than or equal to 1, right? So the less than is not going to work, I think. Okay, let me think about this a little bit. This is greater than or equal to 1. The opposite of that is less than 1. And if we say at least 1, that means existential. So when we invert that, it becomes for all. Okay, so that means that we are saying for all pigeonhole.
They have.
Yeah, so it's not gonna, I think we have to change this to that and that. Okay, that makes it a little bit easier. Okay, so when we invert this, we end up with all pigeonholes have at most one pigeon. Does that make sense? If I negate this statement, if I say it is not the case that at least one pigeonhole has more than one pigeons, if I negate that, would that be the same as saying all pigeonholes have at most one pigeon in it? Because we're just negating greater than 1, it becomes less than or equal to 1, but less than or equal to 1 is the same thing as saying at most. Is that okay? All right, so now we can prove why this here is going to conflict with this over here. Specifically, it has to do with this. Because how many pigeonholes do we have? We have m pigeonholes. And if we say that each pigeonhole can only have up to one pigeon in it, and we ask what is the total number of pigeons, what would that be? It'll be n, but n has to be less than or equal to or greater than m as a result of this. Less than. Not less than, yeah, less than or equal to, you're correct. So this means n is less than or equal to m. Is that okay? Because we have this many pigeonholes, but we are saying each pigeonhole can have only at the most one pigeon in it. So that means the total number of pigeons can only be less than or equal to the number of pigeonholes. Is that okay? Then you look at this, it is ended with this here because of this end. So now we have the result of the negated theorem. Everything that you're given with, but the conjunction is going to be false. And because that conjunction is false, now we know the original statement is true. Is that okay? Because it sounds really awkward, it is actually somewhat counterintuitive if you look at it from a certain perspective. But proof by contradiction, along with proof by induction, turns out to be two of the most useful techniques when it comes down to theorem proving in the context of computer science. Now, proof, I know we're out of time, but proof by induction is super useful because proof by induction has the same structure as recursion. And when you don't have loops, things are easier to work with. Loop is what makes the automated theorem proving a little bit more tricky, okay? But once you get rid of loops, things are actually pretty easy to work with. So that's all we have time to talk about today. So when you guys go home over the weekend, please read the entire module because what I have done so far is to lay out really just kind of the where the trees are and kind of give you a quick sketch of where the tree branches are. But I did not give you all the pine needles. So you kind of have to go home and kind of stick all the pine needles back into the skeleton of the tree to remake the forest. And I'm going to upload the video.